In this video, we will talk about homework 11 problem 2. So if we have a real and Watson's stationary stochastic process XF and its autocorrelation, it has an autocorrelation R tau. We can imply that if it's real and Watson's stationary, so the tau is its autocorrelation is less than or equals to 0. Less than or equal to the autocorrelation on time is 0. And its Fourier transform is non-negative. So based on, and if it's still a real Watson stationary process, so it can imply that its power spectrum as omega is also non-negative. So based on all these properties, we can try to find the following functions. Have some following functions which can follow this process. So first, for the function fv is equals to e to the power of negative of the absolute value of v. So as we see this function, it can we can see that since for every v which is v became far from the 0, every e to the power of negative, the absolute value of v is less and equals to the e to the power of 0. And besides, it is even as following the shape. Whenever whenever v is positive or negative, it always has the same value, so it is even. And e to the power of negative absolute value of v is Fourier transform as 2 alpha over by alpha square plus omega square. It's also non-negative, so we can see that this one can represent our autocorrelation function of our x-axis. For second, since we also know that its autocorrelation is non-negative because it's larger than or equals to 0, we can see that it can represent the power spectrum. See the second one, the function when sine square of v divided by v squared. And this function, we can see that the sign used to be sine v was odd, but when we got square, it became even, and here is even. So basically it is a even function. And also, for itself, it's always less than equals to its elimination when v gets close to 0, which this part is equals to 1. And for its Fourier transform, it can be represented as this shape. We can see that it is all the part is larger than 0, so which is non-negative. And this part is represent that the calculation is less than equal to the r on 0. So based on these properties, you can imply that this function can used to represent as autocorrelation. And because we know this part is always non-negative, since both we have polar square, we can see that it can be used as the power spectrum density. So for the third one, fb equals to 1 when v absolute value is less than equal to alpha and 0 for otherwise. If we try to find these ones, autocorrelation. No, from this one's Fourier transform, we can see that it can be transformed as 2 times sine alpha omega divided by omega, since it was a rectangular signal. And so, but for this one, it sometimes can be both one is negative and one is positive. So the whole part is not non-negative. So it cannot be used for autocorrelation. But when we see that the all part is larger than 0 because of this definition we define here, so actually it can represent the power spectrum for itself is non-negative.